Hello all. In this video, we'll discuss about BFS traversal of a graph. BFS or BFS stands for breadth first search traversal. So in the last video, we spoke about depth first search traversal, right? So the main difference between DFS and BFS is, let's say you have this graph. So if you take a DFS traversal, how you will do is you will go deepest level possible, like you go from 1 0 to 1 or 0 to 1. Since nothing is present from 1, you come back, you backtrack from 1 to you backtrack to the original node, and from 0 if you go to 2, then from 2 you go to 4. This is the depth first search traversal. Coming to BFS, it's like you go level by level, or you traverse or you visit all the neighbors of your node, and then you go to the next level. Now here, if you take a BFS here, first what you will do is you will visit 0 first. Then let's say I'll visit 0 1. Let me remove this. I'll visit 0 first. So 0th node is visited. And then what I'll do is I'll see all the neighbors of 0. 1 2 3 are the neighbors, right? Then I'll visit 1 2 3. Then post that I'll check the neighbors of 1. uh, if the neighbors of 1 are present, then I'll go to the next level. Then I'll go to 2. I'll see the neighbors of 2. Then I'll traverse the neighbors of 2. Then after 4, like if you have one more node, 4 will be traversed first, and then you will go to the second as another level. It's like a level order traversal. You go level by level. So basically you explore horizontally. It's not like vertical exploration. If you see in the DFS, you explore like this, right? First 0 to 2, 2 to 4, and then 4 to next. You are exploring by depth, which means like vertical exploration. But if you see in the BFS, first you visit 0, then you visit 1, immediately you visit 2, and then you visit 3. So it's like a horizontal exploration, or the level order traversal, level exploration. So if you in if you take a real world application or an example, first what if you a typical road example you can take from Newark. Like from Newark, there are multiple roads present to Chicago, Bentonville. If you have two roads like this, maybe you might have another to California as well. So first, what you will do is from Newark, I'll see what are the roads present. Chicago, Bentonville, and California. But from Chicago also, you might have another roads also present, right? But instead of so in BFS, what you'll do is from New York first you go to Chicago, then you come back to New York, and then you visit Bentonville, and then you come back to New York, and then visit California. So once the first level of roads you have visited, then you go to you go to the roads which are originated from Chicago, Bentonville, and California. So in the breadth first search traversal, you first do the horizontal level traversal, which is also called as a level order traversal. Another name for the breadth first search traversal is level order traversal. So, let's take this example. This is the directed graph, and we'll do BFS for this graph. So the data structure we use here to do BFS is queue. If you remember, in the DFS we used stack, because you in the DFS we have to do the we have to go deepest levels, right? That's why we used stack, but here we use queue. So now the how you have to do BFS is steps for doing BFS or this level order traversal is, I'll write down the steps here and then we'll follow these steps for traversing for the sample graph I have shown here. First, you take Q and you take Q as a data structure, and then we have to take a visited array also, because we should not end up in loops. There might be a chance that like to reach to, we can have multiple routes. So in you, like if you already visited two, then from another part, if you come, if you visit two again, then you might end up in loops, infinite loops. That's why you take an visited array. So first thing is we should use visited array to avoid loops, infinite loops. And then we will take Q data structure while traversal. And the steps here are, first, like you start from your vertex, okay? Start from your vertex and then push the vertex to the queue. Push the vertex to the queue and mark the vertex as visited. Yeah. What you have to do is we mark this vertex as visited, right? Now what we have to do is then pop a vertex. Pop a vertex from, or DQ a vertex from Q. So while dequeuing, what you should do is add the vertex to the result and then push all neighbors and then enqueue neighbors of the the vertex to the queue. So these are the you should do as long as the queue is not empty. So if you see here, first what I have done is, this is a queue data structure. Okay. Now I start from 0. This is the 0 vertex, right? Now what I will do is, here I pushed it to the, I enqueued 0 to queue. And I mark this as a visited. Now I mark this one as visited. 0 is visited. Now what so now I have pushed it. So the next operation what I have to do is, you dequeue this one, you dequeue 0 from this queue. So if you see the result, I'll add result value here. While dequeuing, I should add 0 to the result. So now I have dequeued it. I have dequeued it from the queue. I added to the result. Now I'll see the neighbors of 0. Neighbors of 0 are 1, 1, 2, and 3. So you enqueue 1, I enqueued 1, I enqueued 2, and then I enqueued 3 to the queue. While enqueuing, what I'll do is I'll mark these nodes as visited. Okay. Now this is done. Now next what I have to do, I have to dequeue from the queue. Now I'll dequeue 1 from the queue. While dequeuing, what I'll do is I have to add the result to the result. Let like I'll add result here. So in the result, initially 0 was there. Now I'll add 1 to the result. 1 to the result. So now I'll see while when I dequeue it, instead of, if you see the, like if you see this one, dequeue vertex, while dequeuing we have to add the vertex to the result, and then you have to add the neighbors of the vertex also to the queue. Now I'll see what are all the neighbors present from 1. There are no neighbors, there is no path from 1. So I should leave this. So the next step is you dequeue 2 also from the queue. Whenever I dequeue it, I'll add that to the result. Now what I have to do is, I'll see the neighbors of 2. The neighbors of 2 is, it's just only 4. Now I'll check whether 4 is visited or not. 4 is not visited. So I'll add 4 to the queue. If you see, you have dequeued 2 and you have enqueued 4. Now post this, you have to dequeue for 3 from the queue. Now I have removed 3 from queue. While removing, I'll add 3 to the result. Now I'll see the neighbors of 3. I don't see any neighbor. then leave as is. Now you have only 4 in the queue. Now you dequeue the fourth dequeue 4 from the queue, or you remove a fourth element from the queue. While removing, you will add this, and you see whether there is any neighbor present from any edge or vertex that is not explored from 4. You don't see anything here, and the queue is empty. You stop it, you stop breadth first search traversal here. Okay, this is the breadth first search traversal of a directed graph. Let's see for undirected graph as well. Okay, now this is an undirected graph. This is an undirected graph for which we will do the BFS traversal. So as I was mentioning, let's say I start from 0. Okay, if you remember the steps, first you start from a vertex and you add that vertex to the queue. Now I mark this vertex as visited. So whenever I do this cross mark, this means that it is a visited. So in the visited set or in visited array, I'll put this 0 as visited. Okay. Now what I should do? I should dequeue 0. Now when I dequeue 0, when I dequeue 0, I'll add to the result 0. Then I'll check the neighbors of 0. Who are all the neighbors to 0? 0 to 1 and 0 to 3. There are two vertices. And you see, with is 1 visited? No. Is 3 visited? No. Then add both 1 and 3 to the queue. Done, right? Yeah. Now we have done this. Now let's say we have inserted the neighbors of 0. Now what you have to do is you have to dequeue 1 from here. 1 from q. I have dequeued it. While dequeuing, what we should do? We should add 1 to the result. Now after adding, what we have to do? We have to consider the neighbors of 1. If you see the neighbors of 1, 0 is the neighbor of 1. And 3 is the 5 is the neighbor of 1. And 3 is the neighbor of 1, and 6 is the neighbor of 1. 2 is the neighbor of 1. So out of these, 3 is already visited, right? Because we have 3 is already present in the queue, 3 is already visited. So we will 0 is visited, 3 is visited. Whatever is not visited, we will put those elements in the queue. So 2 is not visited. Put 2 to the queue. I have enqueued 2. I have enqueued 2 to the queue, and 5 is not visited. Then add 5 to the queue, and 6 is not visited. 6, add 6 to the queue and mark these vertices are also as visited. So I have done that. Suppose that what I have to do is we have inserted 2, 5, 6. Now I should remove 3 from the queue. So when I remove 3 from the queue, add 3 to the result. Okay. Now you see whether is there any vertex from 3 that is not yet visited. Now there are the neighbors of 3 are, you have this 1 as neighbor, you have 2 as a neighbor, and you have 0 as the neighbor, and you have 4 as the neighbor vertex of 3. But out of these, 0 is visited, 1 is visited, 2 is visited, only 4 is not visited. So you will add 4 to the queue. So I have added 4 to the queue and marked 4th vertex as visited. Now you have done with this. So the next element present here is 2. You remove 2. Whenever I remove it, I add it to the result as well. So from 2, you see whether is there any vertex that is not explored. If you see, there are multiple edges present from 2. 1, and you can see 5th vertex, and you can see 4th vertex, 3rd vertex, but these are already added to the queue. These are already visited, so you need not add it again. You just remove it and add to the result. So I have done the same. Now let's go to 5. You dequeue from the 5, add it to the result 5. Now see the neighbors of 5. So if you see the neighbors of 5, 1 is the neighbor of 5 and 2 is the neighbor of 5. But these are already visited. So you need not add anything to the queue. Now when you remove 5 from the queue, you have 6 and 4 left in the queue. Now you dequeue 6th element from the queue. Add it to the result. Okay. Now when you now check the neighbors of 6. 1 is the neighbor of 6. 4 is the neighbor of 6. There are two edges that are going from 6, right? 1 and 4, but these are already visited. So no need to push anything to the queue. Now there is only one vertex present in the queue, 4. Now what you should do is you should dequeue it. Whenever I dequeue it, I will add 4 to the result. Okay. Now I added 4 to the result. Q is empty. Now, there are 3, 2, and 6. These are all the neighbors of 4, but these are already visited, so no need to add to the queue. Now Q is empty. So our operation is done. So, after doing the breadth first search traversal, you have got this. Like this is not a single solution. Now, if you see, whenever you are adding, when you dequeued 0 and added the neighbors of 0 to the queue, you added 1 and 3. Instead of that, you would have added 3 and 1 as well. You would have changed the order. So let's say if you would have added 3 and 1, then our result would have been 0, 3, 1. So when you add 3, then 3 is the first, you will push the 3 neighbors of 3 are like 2, 4, right? When you push 2, 4, let's say I have pushed 2, 4. Now when we explored 2, then you would have got 5. Then you would have got 5, and then you would have got 6. So what I like how I calculated this is, now here if you see, you have added 1 and 3. Now instead of 1 and 3, I would have added 3 and 1 as well. Like in the queue, I would have added 3 and 1 as well to the queue. So when we add 3, 1, if 3 is the element that comes out from the queue first, so in that case my result will have 3 and then 1. So when 3 comes first, you will explore the vertices of 3, right? So three vertices are 2, 4. Let's say I added 4 comma 2. You would have added in any order. You can add 2 comma 4 or 4 comma 2. Let's say I added 4 comma 2. So in that case, what output you will get? 0, 3, 1, 4, 2, right? So 0, 1 comes first. When like 4 comma 2, when you dequeue 1 from the queue, then you will add 5 here. Okay. Now when we this is the first element. When we dequeue 4, then 6 gets added. So our breadth first search traversal would have been 3, 1, 4, 2, 5, 6. 3, 1, 4, 2, 5, 6, because it depends on the order which you insert. Now we even here, instead of here we added 1 comma 3, here you have added 3 comma 1, right? Now when we dequeued 3, instead of adding 4 comma 2, I would have added 2 comma 4 as well here. This order would have got exchanged. So in that case, my when I have added 2 comma 4, then mine would have been this one. This result would have come 0, 3 comma 3, 1, 2, 4, 5, 6. So you don't get a single output for the breadth first search or DFS. It depends on the order you start exploring it. So yeah, that's it about breadth first search traversal. If you could talk about the time complexity, you are exploring all vertices and the all edges once, right? So our time complexity would be order of v plus c. Order of v plus c. This is our time complexity. This is time complexity of breadth first search traversal. Yeah, that's it about the breadth first search traversal. We will talk how to detect cycles in both directed and undirected graph in the coming videos. Thank you.